On this example, the process is the same. We want to find the same base, but now we have a quadratic on the exponent. So we need to find the same base. So we're going to start by rewriting 9 as 3 squared. Then we're going to substitute that on the equation, turning that 9 into 3 squared. So that's what's happening here. 3 squared raised to the power of 1 minus 2x. And then we just have to multiply the 2 by the 1 minus 2x. And we end up with 3 raised to the power of 2 minus 4x. Now that we have the same base, it's a matter of using the one-to-one property, meaning that we're setting the exponents equal to each other, and we want to solve for x. But the deal here is that we're going to end up with a quadratic. So this is a one-to-one property, and in order to solve a quadratic, you have several options. You can factor, you can use the quadratic formula, you can complete the perfect square. So that's up to you, depending on the kind of quadratic you end up with. In this case, if we solve for x, you're going to end up with the following. If you set the whole thing equal to 0, and then we'll try to solve for x on each factor. In this case, we're going to end up with this equation right here. So we're going to try to see if we can factor it, finding two values that multiply to -6, and when you add them, you get -5. So those values are -2 and -3, and then you have to set each value to 0, and that way you'll get both the 2 and 3 as answers. And if you want to prove your both answers, you would have to substitute the answers on the x. Usually I use this version of the equation.